Hello, this is the explanation video for numerical computation project. So the project is a program that finds the eigenvalues and eigenvectors of a matrix. It is made from scratch with a lot of NumPy because I'm too lazy to write for loops. Here are the references. You can check it out if you have access to the notebook. Let's go through the notebook. So at the top right here, we have some import statement, doesn't really matter. And the rest of the notebook is separated into three-ish parts. So the first one would be power method. The second one would be shifted inverse power method, and the last one is the Gershgorin circle theorem. So let's get started with the first one. So the first one is the power method. It is an iterative algorithm that is used to find the eigenvector that corresponds to the eigenvalue that has the highest magnitude. And this is the update rule for the power method. Basically, A is an n by n matrix, BK is an n element vector, and this fancy term here is basically the magnitude of the element of the vector that has the highest magnitude. So for example, let's say we have vector v, which is 1, minus 7, and 5. The magnitude of the element that has the highest magnitude would be 7. So basically, you can find this by taking the absolute value of every element and then just taking the one that has the highest number or the highest value. And the first guess, the B0, has to be non-zero. And it converges when the update rule doesn't change anymore. So basically, you can check that by checking if you multiply your current guess by A and then you scale it down by this, then you should get the previous guess. Now, once it converges, you will end up with the eigenvector of A that corresponds to the eigenvalue that has the highest magnitude. To find the eigenvalue from this, you can scale down the eigenvector V so that the highest, so the element with the largest element is 1. And then you can multiply A to that vector, and then that element that used to be 1 will be the eigenvalue. So here's the proof of the power method. So basically, let's say we have matrix A with eigenvectors v1 to n with corresponding eigenvalues lambda 1 to n. Let x be written as a linear combination of the eigenvectors. So x is an arbitrary vector. It's basically a random vector that we choose to be our initial guess, and then we can write it as a linear combination of the eigenvectors. And then we can multiply a to both sides, so a times x and then a times each of the term. And we can do it k times, where k is a pretty large number, and we're going to end up with this. And because we know that vectors 1 to n, vectors v1 to n are eigenvectors, and we know that the definition of eigenvalue and eigenvector is this. We also know that if lambda is an eigenvalue of a, then lambda to the k is the eigenvalue of a to the k. So we can kind of quote unquote simplify it to this expression here. We can let lambda 1 be the eigenvalue of A with the highest magnitude, and then we can factor it out from this expression to get this expression instead. And because we know that lambda 1 has the highest magnitude, it's basically going to dominate the rest of the terms, making like the rest of these terms become 0, and we're going to end up with this, which is basically A to some power where k is very big, multiplied by an eigenvector that is scaled by some number. This means that we can just choose a random vector x and then multiply a to it many times, and at some point you're going to get the eigenvector of that. And as for finding the eigenvalue part, This is basically because this is the definition of the eigenvector and eigenvalue. So if an element of an eigenvector is 1, when you multiply that vector by a, then it's going to be lambda times 1, because when you multiply a matrix to its eigenvector, then it's going to scale by the eigenvalue. So it's going to be 1 times eigenvalue, which is the eigenvalue itself. So this is the code. I'm not going to explain it. You can read it yourself. So here is a matrix, a random matrix. And as you can see, we can use power method on it. And you're going to end up with -3 and then an eigenvector. And here, the eigenvector is this value. And if you multiply it by a, you get this one, which is the same as if you were to multiply it by the eigenvalue. Now, the problem with power method is that it only finds the eigenvector that corresponds to the eigenvalue that has the highest magnitude, because of, it has to dominate the rest of the terms. Now, the problem is some matrices may not have just one eigenvector or eigenvalue. So we have to find a way to find other eigenvalues and eigenvectors. And that is where the shifted inverse power method comes in. Instead of finding the eigenpair that corresponds to the eigenvalue that has the highest magnitude, we can instead find one that is closer to a number alpha. So it's very similar to the power method. This is the update rule. Basically, it's basically the power method, but it's performed on this matrix instead of the matrix A. And alpha is the initial guess for the eigenvalue, also known as the shift. The rest are basically the power method, and it gives us the eigenvector that corresponds to the eigenvalue that is closest to alpha. And once convergence is reached, we're going to end up with eigenvector v. That is the eigenvector of this matrix, and also a, which we're going to prove later on. It's going to correspond to the eigenvalue lambda minus alpha to the power -1. And if we let this value be omega, then we can do some algebra to figure out the original eigenvalue, or lambda. Okay, so here's the proof for the shifted inverse power method. We can start with the definition of the eigenpair, and then we can pull some property out of thin air and then subtract both sides with alpha times identity matrix times vector v. Now, because the identity matrix is omitted from the right-hand side because it doesn't really do anything. And then we can simplify it down to this expression. And once we do this, we can do kind of like cross multiply them, or basically multiplying the inverse of both terms to both sides. And you're going to end up with this expression where these two are the same thing. Now, this is basically the definition of the eigenpair, but instead of a, it's going to be for this vector instead. Now, because we started this whole thing with vector v, which is the eigenvector of a, so it means that even after all of these fancy manipulations, vector v is still going to be the eigenvector of a. Now, we can use the power method on this new matrix and new value. So we can let b be the matrix that we manipulated from a, and omega be the eigenvalue that corresponds to b. So we can write x as a linear combination. So basically the same thing as the power method. X is a random vector, and then we can do the same thing, but instead of the eigenvectors of a, we can do the eigenvectors of b. And because this is similar to the regular power method, we're just going to skip a bunch of stuff, and then we're going to end up with this when we multiply x with b so many times, k times, and k is very big, which is basically equivalent to this expression right here. And from here, we can kind of do algebra to convert it back to fit A. So x is going to transform into the eigenvector, and the right-hand side is basically this. As for y, lambda is the eigenvalue that is closest to alpha. For the power method, the reason that we're able to find the eigenvalue lambda is because it has the largest magnitude and it dominates the rest of the terms. Now, if we do 1 over lambda minus alpha, then the closer lambda is to A, the term 1 over lambda minus alpha is going to shoot up to infinity. So it's going to be the dominating term instead. So here is the code for the shifted inverse power method. I'm not going to explain it, but it's basically the same thing as the regular power method, except instead of A, you use the inverse instead. And yeah, you get, so if we start from 1.1, then we're going to end up with eigenvalue 1 and its corresponding eigenvector. And then, as you can see here, it works. Now, our problem becomes, how do we choose a good alpha value then? So we can use the Gershgorin circle theorem. So basically it says that the distance between an eigenvalue and a diagonal entry of a row of the matrix is less than or equal to the absolute sum of the remaining entries. So let's say we have this matrix, which is the one that we've been using this whole time. There is going to be an eigenvalue whose distance is 24 away from 5. So basically 5 and is the diagonal entry, and then these is the absolute sum of these two entries are going to be the maximum distance of the eigenvalue away from 5. And the same thing for 1 and the same thing for minus 11. Now the proof is kind of involved, so I'm just going to say that the proof is by magic, but there is a proof written out, so if you're interested, please read it. It's part of the notebook anyway. Yeah, so basically we do some manipulations with the matrix multiplication, and we end up with this, which is basically the theorem itself. And here's the code. I'm not going to explain it again. Okay. Anyway, moving on. So we can put everything together into a function called EigenSeeker, which is also the name of the project. So basically what it does is it finds the alpha values using Gershgorin circle theorem, and then it performs the shifted inverse power method on the given alpha values, and then add it to the set. Well, the quote-unquote set. It's actually a list, but you know. And then finally, you will get a tuple where the first one is a list of eigenvalues and the second one is a list of the eigenvectors that corresponds to the eigenvalue. And here's an example. We're going to use the matrix that we used before. Using NumPy's eigenvalue finder, we end up with 1, minus 3, and minus 3. So basically just 1 and minus 3, right? And this is our home-baked eigenvalue finder. So we get 1 and minus 3. Now for the eigenvector, we have eigenvector, this one that corresponds to eigenvalue 1, and we multiply it by A and by the eigenvalue, and you get the same thing. Same thing for the eigenvector that corresponds to eigenvalue minus 3. And yeah, it works. Anyway, so in conclusion, this function is still not very good or accurate. The performance is probably not very good. But I think for a home-baked one, I think it's good enough. And, you know, you'll end up using the professional one by NumPy or SciPy or whatever library is fancy in the future. But anyways, thank you for watching, and I'm going to go to bed now. Bye.